This video is the first part of Gauss law, and it is going to focus on the concept of electric field. This is going to be our learning outcome, to define and calculate the electric flux through a surface. And we will state Gauss law for electric field and apply the law to solve problems. Finally, we will state Gauss law for the magnetic field and interpret the law. Let's go through what we've learned so far about charges and electric field. First of all, charges. We know charges create electric field around them, and electric field are lines of force. Charges create a field or force around them, and force field is represented by field lines. So field lines show the direction of force on a positive charge, and field lines are drawn starting from the positive charge to the negative charge. The closer the field lines, the stronger the force, in the field. That is, the stronger the field strength. Electric field strength is the force per unit charge at a point in an electric field of a charge. That is, the electric field strength represented by the capital E, and it's a vector quantity, is actually the force divided by a charge in that field. Now, force field is quantified as the force strength represented by field lines. So, indeed, the electric field strength is what we represent by the field lines. So, sometimes the electric field strength is also referred to just as the field, simply as the field, or simply as the strength of the electric field in some context. Imagine an electric field represented by the field lines in the orange color. We can also imagine a plane area that is crossing the field. We define the electric flux as the product of the electric field and the area in which the electric field crosses. So the flux that is represented by the Greek letter phi is equal to the electric field itself multiplied by the area through which the electric field crosses or passes through. In several situations, the field will not be perpendicular. The field will not be perpendicular to the area. It is possible this area, surface area, will be slanted, or it will be inclined to the direction of the field. If that happens, then we need to modify the formula for calculating the electric flux. It will be the electric field multiplied by the area, the total area, multiplied by the cos of an angle the area makes with the direction of the field. So in this case, it is 90 degrees. The plane is making an angle of 90 degrees with the electric field. But 90 degrees is not what we are using. We need to draw a vector that is perpendicular to the cross-sectional area, the area that we are concerned about. And the angle between the electric field and that vector is what we are calling the theta here. So indeed, it will be, if this surface area is 90 degrees, then the theta we are looking for here will be 90 degrees minus 90. For this particular situation, it will be 0, cos 0. If cos 0, then it will be 1. Then we come back to the first equation for electric flux. Now, in some situations, we may have to use vector for the electric field, and area, we need to modify area, which we already know as a scalar quantity, to become a vector quantity. And we do so by simply multiplying the scalar quantity of the area, that's the magnitude of the area, by a unit vector that is perpendicular to the area itself. If we have the area element, area vector, then we can dot product it with the electric field and get the flux. We'll try to see how we work that one out in some examples. What I also want you to keep in mind is that the unit for electric flux is Newton meter squared per coulomb. If we are using the SI units, then it will be the Newton meters squared per coulomb, or simply put, volts meter. Electric flux is proportional to the number of field lines crossing a surface. This will be a simple understanding that you can keep in mind. Let's take our first example. A vertical electric field of 2 by 10 to the power 4 Newton per coulomb exists above the surface of the earth during a thunderstorm. So I've represented that electric field with the black parallel lines that are also vertical. Now we are required to find the electric flux through a car covering a rectangular area measuring 6 meters by 3 meters. So this is the rectangular area occupied by a vehicle, a car. We don't need to draw the whole car. What we need is the area it occupies. This one is on the horizontal surface. So if you want to calculate the flux, it will be straightforward, a simple way of calculating it. Then we come to a second situation whereby there is a hill with the same surface area. The slope of the hill is inclined at 10 degrees. This is 10 degrees. So we are going to calculate the flux through that same surface, this time around, which is inclined. Let's see how that is done. For the first one, we are talking about the surface area being perpendicular to the direction of the field. In other words, if we draw a vector that is perpendicular to the surface, then that vector will have an angle of 0 with the direction of the field. So this vector is parallel to the direction of the field. In that case, cos the theta that will be needed, if we need to include the theta, will be 0. So cos 0 will be 1, and we are left with this simple equation here. So we just substitute our values, calculate the area, which is 6 by 3, 18 meters squared, and then substitute the area here. Thus we multiply the area by the electric field, which is 2 by 10 to the power 4 times 18, and that gives us 360 by 10 to the power 3 Newton meters squared per coulomb. We come to the second one. It's 10 degrees. If it's 10 degrees, then a vector that is perpendicular to the surface will also form a 10-degree angle with the electric field. So this angle, which is 10 degrees, is what we will need to do the calculation. That will represent the theta here. It is this angle, please. Not necessarily what is here. It is the angle this vector makes with the electric field. Indeed, because this one is a smooth surface and it's already inclined, and this one is vertical, it will automatically mean that this angle is the same as this angle. Alright. So how do we calculate the flux? Since the surface is not directly, is not perpendicular to the electric flux, we need to find the angle here, which is 10 degrees, and then include it in the calculation. So we have the electric field, which is 2 by 10 to the power 4, multiplied by the area, which we've done that one already as 18, and then multiply it again by cos theta, theta being 10. And we see that there will be a reduction. This is the second question. This time around, we have the area vector given as a vector in vector notation. That's 2I plus 3j meter squared. Then we've been given two folds. The folds are also in vector notation. We are supposed to find the flux due to this electric field and then the area. How do we do it? This time around, because the electric field is in vector and the area too is in vector, we just use this form for calculating the electric flux, and it can be done straight away. let me use this opportunity to help you appreciate how we do dot product. 4i and 3j are not alike, so if we dot multiply this one, we get 0. If we dot multiply this one, we get 8. That's 4 times 2, and the i's become 1. So we have 8 here, and the flux will actually be 8 Newton meter squared per coulomb, or 8 volts meter. Let's see how the second one also goes. So we do expand, and we are going to get negative 7k dot 2i. These are not like. We also come here, negative 7k dot 3j. These are also not like. So if you dot multiply unlike terms, unlike vectors, then you are going to get 0. Let's look at the third question. Now there is a box, and the box has 6 surfaces, but there is an electric field traveling from one side of the box and emerging from the opposite side of the box. We are expected to find the electric flux through each of the 6 surfaces of the box. Now the field strength is also given as 10 Newton coulomb. How do we find the flux? Again, we use our usual concept. That's the flux being the product of the electric field and the area cos theta. There are no vectors given us, so we don't worry ourselves with vectors now. We just need to see the field through which surface. Let's take, if you look at it carefully, the surfaces have been numbered. The surface in which the field enters has been numbered N1, and the surface in which the field emerges out is N2. And all the other surfaces are numbered N3, which is the surface behind there, N4, which is the surface facing S, N5, which is the surface on top, and N6, which is the surface at the bottom. So the field is moving in this direction. The flux through this surface, because this surface is perpendicular to the field, the unit vector is parallel to the field. You can see the unit vector that is perpendicular to the surface. Yeah, so the angle, if the electric field is moving in this direction, then the angle will be 180, because this one is moving in the opposite direction. So the angle from here, if we should start from the direction of the electric field, then we move all the way to this side, then we are talking about an angle of 180 degrees between the electric field and the unit vector of this surface. We use that one and we get a negative value here, which is negative 0.004. So I did not bring the units. It is Newton meter squared per coulomb. We can do similar thing for this one. This time around, the electric field is in the same direction as the area unit vector, and the angle is 0. So we just do the calculation and we get 0.004 Newton meter squared per coulomb. The flux for all the other 4 surfaces are the same. Why? Because the other four surfaces are all parallel to the electric field. In other words, the unit vector of their surfaces are at 90 degrees to the electric field. You can see that this one is 90 degrees to the electric field. If the electric field is in this direction, then this unit vector, the top surface, it will have a unit vector which is 90 degrees to the electric field. So that will make the flux through this surface to be 0. Likewise, that's for the N3, N6, and then N4. Everything else will be 0.